This, in essence, starts on page 846 and carries through the end of the chapter. We are only going to focus on the English fits. There are metric fits. They both work the exact same way. The terminology switches just a little bit. So if you do a metric, you can come back in here and work on that. We'll stick with just the English portion of this. Now, just as a little bit of background, normally I would not teach this in this course because fits, as they are applied in this chapter, are strictly a mechanical engineering discipline. And I would put that in Drafting 150, which is over the summer, where we focus on just that discipline. I've decided to keep this in here quite a while ago for the strict reason that every discipline has things like this, where they have specific documented information on how things are built and done. Doesn't matter if you're doing civil, you're doing plumbing, electrical, whatever. They all have this. So this is a good look at things you can expect in any discipline when we get ready to do something. Like if I'm framing a corner, they're pretty much done the same way. If I'm tying rebar, if I'm doing whatever, if I'm doing switching, resistors, whatever. We have these set principles that are documented on how we use them. So this is a picture of that. But keep in mind that what we are going to talk about is really only applied in the mechanical world. The fit types are starting on page 846. There are 3 fits that are listed in this chapter, and they cover all the 3. When we do these, we have a clearance fit, which is taught down here. You have an interference fit here, and you have a transitional fit. Now these are developed for mating parts, namely shafts and holes, because we use those everywhere. In fact, whenever we have a powered device, almost always it starts in a rotary fashion from an engine and then moves to a linear type of motion that we use different devices to move through, like linkages or gears or something of that nature. So let's look at the 3 types of fits here. When you're looking at these basically, this is where you aren't reinventing the wheel. So we look at a condition and we say, I want these 2 mating parts to operate in a certain way. I may need to apply maintenance to them, I may have safety to them, I may have joining characteristics. These fits take care of all of that. Look, you can see your hand sitting on the desk. Kind of funny anyway. So when we're looking at it, you've got a clearance fit. When do we use a clearance fit? Basically, if I use a clearance fit, when I join these 2 parts, they will never interfere with each other. So I can put them together. So here's my shaft and hole. Now, this is a clearance fit with these 2. So as I put them together, they will never interfere with each other. The hole will always be bigger than the shaft. That's what we call a clearance fit. Okay? When we got an interference fit, that's the next one. What that one states is basically when I take the hole in the shaft, they will never fit. Okay? I can't just put them on like this. I have to use mechanical means to throw them together. Now the transitional fit, the last one, is a combination of the 2. It may slide right together or it may not. Now when do we use the 2 or the 3? And what's determined on those? In essence, like I told you yesterday, you won't make this call coming straight out of college. Somebody will bring you through the process, and then you'll start making those calls under guidance. Once you have some successful completions, then you would probably start doing these once you move to a designer level. So let's kind of talk about what each one is. Clearance fits. You're going to have 2 types that are spec'd out. And you're going to like these things. I mean, because in essence, this is all the work's done for you. All you have to do is look up the documentation. So when you do a clearance fit, you're going to have 2 types of fit. You're going to have an RC fit. This is the loosest fit possible on these scenarios. And basically, it means for running clearance. Okay. Now, when do we use RC fits? Generally in a dirty environment. Okay. We want to put these things together. We don't want to use mechanical means. and we're going to have dirt or something in it. Conveyors, good example. They're pretty dirty, right? Because they're generally hauling dirt, rock, grain, stuff of that nature. And a lot of that spills out and gets into the working mechanisms of a device, and we want that stuff to kind of clear itself out. So we need a little bit of room for those things to work. That's a clearance fit. Additionally, if we need maintenance on a part, remember interchangeable parts, so we've got, once something wears out, we're going to pull it apart and replace parts. This is a good fit because we're going to perform maintenance on it. Okay, so you're looking for RC and LC. RC is very loose. You're going to see these have probably 5 to 1,000 air. 5,000s to 100 air. These right here are very tight, but they will still fit together. They can be what we call line to line. You don't see one of those on there. When I say line to line, they're basically the same size. So the hole would be the same size as the shaft. Now these right here, we're going to use these when, again, we're going to perform maintenance on the part, so we've got to tear it apart at some point in time. But we need it to operate at some high speeds or something, so we got to get rid of some vibrations. We want them to fit a little tighter. Okay. When we do a transitional fit, these are all done with T's. Okay, so you're going to see these. Basically, very tight, because it can be an interference fit, it can be a clearance fit. Okay. Tight fit, we can still get it apart as a general rule. Okay? We don't really need a whole lot of special devices to get them apart. You might use a small hammer to knock it off or something of that nature, but you're going to get rid of all that vibration that occurs in these. The last type of fit, are we good on this? I see a bunch of people writing. Should I
Yeah, leave it up for a second, please.
Okay. The last one is the interference fit. You're going to see these nomenclated as an N. Now, why wouldn't I use an I when I use this?
Because it's a...
Yeah, we never put an I by itself, right? Because it can be confused for a 1. And these will go on drawings. Many times we'll go ahead and do a shaft and then just put on there, do an LC8 fit. And then the machinist will go to the machiner's handbook and know what sizes they are. Okay, they work off of a basic size. Interference fit, okay, you have an LN. Okay, this is a lot like a transitional fit. It's very tight, but we can still usually get things apart, okay, without destroying things. Okay. So again, another thing for maintenance, but we need high operating speeds or something like that, so we don't want things banging and flying apart. Okay. That would be an interference fit. If you go with an FN fit, this is the tightest fit of all. This is generally used when we don't have a method of joining two parts, because the FN fit is a joining method. It's a very tight fit. These will never go together. We usually have to put mechanical means to join them. Okay, so in essence, we're going to shove them together, remove material from both, and it's going to be locked on there. Okay? So it's a joining method per se. We can't get it off without destroying the part. And that's kind of the thing. So if I've got a shaft and I'm trying to get a gear off it or something, I'm basically probably cutting the shaft. Okay? Because I can't get it off and still reuse it. Okay? And those are our FN fits. Okay? Now, when we use these, we got a little process that we run through, and this is what your supervisors will use right at the start. So here's how you use them. Okay, keep in mind, what we're talking about here is a cylinder and a positive and negative fashion, shaft and hole. Okay? Power device. So first thing, you basically determine the basic size. What's our basic size? Theoretical perfect size, right? So we come in and say, okay, well, I'm going to use a 3/4, or I'm going to use a 7/8 or a 5/8, and that's going to be the basic size. Now that will apply for both devices. That's going to apply for the shaft and the hole. Okay? Now, once we determine what the basic size is, or what we're driving everything with, and this can, by the way, this can be determined many different ways. Depends on how much torque we're running, what we're trying to drive. That's going to determine size, right? Next thing we're going to do is we're going to determine the type of fit. I put a note on here, early in your careers this is given to you, and it most certainly is. But once you get a little experience, you might make these calls. And what are we determining for the type of fit? What's the operating conditions? Do I have safety concerns? Will I perform maintenance on this machine or not? Those are really the big ones, but we talked about those yesterday. Last thing we do, once we determine the type of fit, then we calculate all our sizes. We make sure we analyze them at MMC and LMC. Maximum material condition, least material condition. That's going to give us the endpoints of these operating conditions. And we then, like we talked about yesterday, we may or may not assume everything in between those is going to work good or not good. But we can make some assumptions. Last thing, we draw and dimension our parts accordingly. It then goes to the craftsman, and they perform the building of the part. Any questions on that? Now, how does this affect you as a drafter? Okay, generally, you're coming in somewhere in this area right in here. Somebody sketched this out, they've determined the sizes, they've determined the type of fit, and they'll give you a little sketch. And so they might throw out something, depending on their sketching skills. They might have something like, here's a shaft, and say, hey, I want you to go ahead and do this, and we're going to do a 3/4, and I want an RC1 fit. And go ahead and draw this up and dimension. That's all you need to do this. You can then dig up the rest of the information, and you can draw and dimension accordingly. So when you get this sketch, your end view might look like something like this. Okay, where I would come in, since it's a shaft, it's going to be smaller. So let's say I now have a nice drafted drawing where I see that view, this view. I'm going to go ahead and put my dimensional information on here. This might be 0.691. And then I might have plus 0.006. I'm kind of doing this bad. I wanted this to kind of look like a drafted drawing. Let's do it this way. So this would be plus 0.006 minus 0.001, and my diameter is 0.690. Okay, and that might be your ended drafted drawing. We would still need this dimension here also, correct? Based on that one little sketch and that one little note, you could then draw this up. Same thing would go on with the hole. Okay, in essence, we'd draw a collar, however we're attaching it, and then they just say, hey, I want this hole to be an RC1 fit. Keep in mind that these are two mating parts. So if I'm using an RC1 fit on the shaft, what do I have to use on the hole? Same thing, RC1 fit. Okay, because I need them toleranced together. These are meant for mating parts. Okay. Now, how do you determine these numbers? In essence, the end of your chapter has this sheet on it right here. And let me just give you the page number for this. There's not very many past where we're at. And of course, now I can't find it.
861.
873? Thank you. Yeah, 873, 874. They have two examples on them. This is actually copied off of 873. Yours says 733, but that was an older edition. table hasn't changed. All right, so this table is a handy way for you to determine all of these sizes. And I want you to work through a few of these, so I copied this for you. And let's run through how we use it.
Okay, cool.
So in essence, all this sheet is going to do is keep you organized so that you can figure out all the numbers you need for drawing and dimensioning. Now, it all starts, like I mentioned, on a basic size. So on this sheet right here, your basic size is spec'd out in the top. It's 3/4. Okay, they're showing a 0.75. That's for the shaft. It's also for this hole over here. Now, what we're then going to do is look at how our operating conditions are. So you've got 3 fits that are given across the top. You've got an RC4 fit. That is a clearance fit, right? This is our loosest fit, so running clearance. Then you have an LT, which is your transitional fit. And then you have an FN, remember that's our interference fit that is the tightest. This is considered a joining method. Now, after that, where do we do? We go to our good friend, the Machinery's Handbook. This information is in here. Okay, so again, we're gonna have to kind of pair up on this. Do we still have all these books out? There's a couple that were put back on the thing over there, so let's go ahead and find this information. If you look in the, I think if you've got the 28, it's thumbed, right? And I think it might have a thumb 4 fit. What you're looking for in there, let's make sure we can all get to the same page. And you're going to see these numbers be slightly different depending on the version you're using. So you're looking for a chart that across the top has your different fits. And we're going to do the RC4 fit. Now go to the index at the end and look under fits, cylindrical.
Yeah. Table contents for machine.
Oh yeah, these ones are totally. Which fits?
Cylindrical.
Cylindrical?
Yes, for cylindrical devices, because we're doing a shaft and a hole. When somebody's got it found, maybe call out the page number and version of Machinery's Handbook.
28.
28 is what page?
640.
640?
Oh, hey look, somebody bookmarked it.
You're in the 26th edition. What page are you? Did you find it?
Let's see, I want to make sure we're on the same page here.
I've got my, actually, thing holding my page open. So you're going to be finding the RC4 fit. These will be at the front of the chart because it goes clearance fits, then it goes transitional, and then it goes interference.
Okay, RC4, 634 and 635.
634 in the 26th edition. You're in the 28th. That was 6, what was that one, Lisa?
640.
640? Juan, Jesse, you
My
there?
pencil. Uh-huh. You stole my pencil.
Oh yeah, that's yours. This is mine.
I see how it is.
didn't
Glasses are off,
notice.
Cheryl. Is your head feeling better today? Okay. Okay, we all there? All right, now, whenever you're using these charts, you'll get some experience on them. You'll want to read the notes underneath the figures and stuff. This one basically will tell you that every number on here needs to be divided by 1,000. Okay, so these numbers, we're going to have to adjust them. They did that so that they could fit them all together. So the way you use this chart is you come down the left side where it says nominal size on your ranges. And you'll notice the first one's from 0 to an 8, the second one's an 8 to a quarter, quarter to a little bit less than 7/16. But you go down and find where your range is. We're doing 3/4, which is 0.75, so our range is right here, 0.71 to 1.2 approximately. That might be different in different versions. I've got the oldest version in the room.
Yeah, I got 1.97.
You got 1.97 on yours?
Oh wait, no. Sorry, I was looking at the bottom.
Yeah. All we want to do is make sure our basic size falls in this range. Now from there, we just follow it over to our fit. So I'm going to come over to the RC4 fit. Now it's got your limits given for you right here. The hole is the first one, the shaft is the second one. So we're going to use these numbers. Remember, when this one says a number of 1.2 for my upper limit on the hole, that's divided by 1,000. So this is really 0.0012. 0 divided by 1,000 is 0. Okay, that one's easy. The next one, you got a negative 0.6. That's really negative 0.0006. Okay, so divide all these numbers by 1,000. Or that's on the wrong one, it's 0.8. All right, so let's show, and I really like this chart at the end of the chapter because it's going to help us out. So we're going to go to the first one. Now, on this chart, notice this first section is for the hole. Okay? So what's our nominal size? That's our basic size.
0.75.
Okay? And keep your decimal places here, 0.7500. Then it's saying, what is your limit? And this is your upper limit. So you would look on that chart, and we're dealing with the hole. I've got a plus 1.2. Does everybody have that same number?
Yes.
Okay, so this is a plus
That's what-
0.0012. I'll kind of zoom in on this a little bit. Okay. So it's a plus 0.0012. Does everybody understand where I got that number? Then we just do the math, and it's saying what's the upper limit of the hole? So this is 0.7512.
Wait, where'd you get that one?
I added the two above it.
You add them together.
That's why it's got a little equal sign on there.
Oh yeah.
So when these holes are machined, the biggest hole I can get is 0.7512. Now, keep in mind, if I've got a big hole, is that maximum material condition or least material condition for the hole?
Max. Because you said the biggest.
When a hole
Least.
is biggest,
Least.
it has
Oh,
the least
yeah.
amount of mass. So this is the least material condition for the hole. Now, let's look at maximum material condition. So again, I've got my nominal size, which is 0.7500. My limit on this one is 0, right? Okay, so that's 0.0000, so it can be 0.7500. This is maximum material condition for the hole. So I will take from the machinist, when quality control gets a hold of this, they'll measure the hole and it needs to fall from 0.7512 to 0.75. Any size in between is an acceptable hole. So you're figuring out your tolerance limits here. Now, then we move to the next part. This one has the shaft with it. Again, what is our nominal size? It is 0.7500. So we're using the basic size for both devices. What is our upper limit on this?
Negative.
Negative.
So it is, yeah, pay attention to these signs, minus 0.0008. Do the math on that, I think you get 0.7492. I hope I did that right. Somebody ought to grab a calculator, maybe check me. I never
That's
took
right.
my shoes off and count this up.
That's right.
Toes. We're good.
You're good.
Okay. Then we're gonna do, that's the upper limit, so the biggest the hole, or the shaft can be is 0.7492. Yes, Dave?
It should be 0.008, not the 3 zeros. Correct?
No, I had
Take
it.
0.8 and divide it by 1,000.
Thousands.
Take, it's a.
Oh, you're right, you're right.
Mine says minus
Okay.
0.8.
Okay.
Do you see the 0.8?
Yeah.
And then if you divide that by 1,000. So I think maybe you missed the point, the decimal point before it. Okay. So then we're going to do the, now keep in mind, this is the largest shaft. Okay. So that's maximum material conditions. Then we'll do the lower limit, which is again 0.7500. And this time I've got a minus 1.6. So this is a minus 0.0016. Dude, this one's gonna be hard. That's gonna be 4, 8. 0.7484. You might want to check that with a
Yeah, I
calculator.
got it.
All right, so now we've got everything. There's my shaft limits right there. Here is my hole limits, and I just kind of circled them. So now I can see how the things operate. Remember, this is a running clearance fit. Okay. So if you kind of look at it, the biggest